then tell you about the polarization fluctuation of the CMB. And so there's a lot of physics in there, so there's a lot of intuition I'll try to convey. Don't worry if you don't understand everything the first time. I think I'm still learning about this after 15 years every time I read about it. And I wanted to advertise that Larissa kindly put a link on the website here. So if you go on the website for the school and you go in the lecture tabs, you'll see a link to a Google Drive folder. And there I'll be putting all the slides as soon as the lecture is done. So you can already find the slides for lecture 1 and 2 in there. And I'll put lecture 3 today. Last time I gave some puzzles, and so I just wanted to, I'm not going to solve them here, but I just wanted to remind you of the puzzles, and feel free to think about them, and we can talk about them maybe in the question session if you have thoughts or guesses as to what the solution might be. So one is the statement that recombination should always happen at the same temperature, and so why is it that in the temperature fluctuations I see there is a term like this, if the temperature should always be the same everywhere? So that's the first puzzle. And the same time is, the second puzzle is, why is the CMB 40 billion light years away when the universe is only 14 billion light years old, 14 billion years old? So you think again about those, and we can talk about them at the question session if you're interested. But so picking up where we left it last time, so if you remember, we were trying to understand the shape of the CMB temperature power spectrum as a function of scale. We had talked about the fact that the CMB temperature fluctuations we see are the sum of the CMB temperature fluctuations that were at the last scattering surface, plus a gravitational potential term that says, for you to see the photons have to escape their own gravitational potential, and in doing so, they can lose energy. So this term we had called the Sachs-Wolf term, and we said that it added up to phi/3, so basically just the gravitational potential. And we focused mostly on this Sachs-Wolf term, this gravitational potential, and we saw that there was a lot of very rich physics phenomenology going on for this Sachs-Wolf term. And so we talked about the fact that there were those bumps and wiggles in the power spectrum related to this acoustic scale, or how far can sound travel between the Big Bang and the CMB. We talked about why there's this overall shape, this amplification here at high L due to radiation driving. And we talked about why there's this peak height asymmetry between odd and even peaks due to the effect of baryons. Yeah, question? Right, yeah, so what I mean is you see the CMB when it's emitted soon after recombination, and you see it because the universe becomes neutral and transparent. And that always occurs at the same temperature everywhere. It's not, say it again, instantaneous? Okay, but even if it were instantaneous, maybe you can think of a toy model where it would be instantaneous. I think this paradox would still be there, I guess. But yeah, we can talk about it more. Okay, so acoustic bumps and wiggles, amplification due to radiation driving, even odd peak height asymmetry due to baryon loading. And today we're going to continue describing the remaining features of this curve. So one is that I talked about amplification, but in reality the power spectrum ends up going down. And so that's one thing we'll talk about. And we'll also talk about these other terms. So the Doppler term here that has to do with velocity at the surface of last scattering. And this term here, which is an integral of how much the potentials change over time between last scattering and us. So again, this is the Doppler term. And this is what we call the integrated Sachs-Wolf effect. Okay, so I'll start with the Doppler term. And a lot of things on this slide, but please don't get alarmed. The Doppler term has to do with velocities, as you can see, as opposed to temperature. But because of conservation of mass, the velocities and the density or the temperature are related. If I have more density here, it's because stuff has been moving towards it. And so by conservation of mass, you can see that the velocities are related to the time derivative of the density or the time derivative of the temperature. And if you remember, we had those sound waves that oscillated in temperature. And so we had this cosine of time with some frequency that depends on the wavelength. That's how density and temperature evolve over time. And so the time derivative of this cosine is just a sine. So the velocity term here and the temperature and potential terms here are out of phase by pi over 2. One is a cosine and the other one is a sine. And the result of this is when you look at the power spectrum of the Sachs-Wolf term in blue, you have those bumps and wiggles. When you look at the power spectrum of the Doppler term here, you also have bumps and wiggles, but they're not in phase because one is cosine squared and the other one is sine squared. So that's the main thing to know about this Doppler effect. Maybe one subtlety that I'll add, and feel free to ignore this, is naively when I have the power spectrum of cosine and the power spectrum of sine, so I get a cosine squared plus sine squared, that should add up to 1. And so naively you might worry that the bumps and wiggles in the Sachs-Wolf would be canceled by the bumps and wiggles in the Doppler term. And in practice, this doesn't happen thanks to some subtle reason about these projects onto the last scattering surface. So I'll leave this slide in the Google Drive as a reference, but that part is a bit of a detail. So the main thing to remember is a cosine squared for Sachs-Wolf, sine squared for the Doppler term, and they're roughly comparable in size. Mm-hmm.
So in this plot, you are showing the autocorrelation of each component.
Mm-hmm.
Is it possible that each component is cross-related with each other, or this is what you're saying that they cancel?
Yeah, that's a good question. I might need to think about this more. You might have a cancellation in that delta times v, but I should think about it. Yeah, thanks for that's a good question. Yeah. So this is all I was going to say about the Doppler term, and I'm now going to move on to this remaining term, this integrated Sachs-Wolf. And so this integrated Sachs-Wolf is an integral between the last scattering surface and today of how much the potentials change with time. And physically, the effect is the following. As you have a photons that travels between the CMB and us, it might encounter potential wells, for example, around the large-scale structure. If those potential wells do not change with time, your CMB photon, when it goes down the potential, gains energy, but then when it re-escapes the same potential, loses the same amount of energy. And so the net effect is that the photon has seen no change in energy. It's like throwing a marble with no friction on a path that has a bump and goes back to the same exact height. The marble accelerates and then slows down back to the initial velocity. But this changes if the potential changes over time. And so that's why you have a time derivative of the potentials there. And intuitively, the idea is your photon goes down the potential and gains energy. If by the point the photon is at the bottom of the potential has disappeared, so say the potential has decayed, then the photon no longer needs to climb out of any potential, and so it gets to keep the energy it gained by going down. So I don't know if that makes sense or if there's any question. Yeah? This is different from lensing, in that lensing is an effect that occurs even with static potentials. And so in lensing, you can think of those marbles going down, curved paths. And so their paths will be deflected, but their energy won't be changed. The energy changes once the potential change with time. Okay, so that's the integrated Sachs-Wolf. Yes? Mm-hmm. Right. So that's a really good question, and that's what I wanted to talk about next. So why would the potentials change with time, and on what scales, and things like this? And so to understand it, I want to go with you through this argument. So when the potentials change as the photons travel through them, we have a net change in the photon's energy. So that's what we just talked about. And so in what circumstances do you get potentials changing with time? And so to understand how potentials change over time, you have to understand the sort of conflict between two effects. So the growth of matter perturbation is a competition between two effects. One is the expansion of the universe, which tends to make things uniform and to flatten the potential wells, so to make them decay. And the other thing is gravitational collapse, when matter concentrates together. This tends to get the potential wells deeper. So you have these two effects fighting. And basically what happens in this fight is that all of the energy density contributes to the expansion via the Friedmann equation. So Hubble squared equals all the energy density. But only the energy density that is clustered contributes to the clustering. And so when the dominant component of the universe is clustered, like in the matter domination era, so matter has an energy density, contributes to the expansion, but it also clusters, and so it fights back by deepening the potential wells. What you find is that the gravitational potentials remain basically constant over time. So in all the matter-dominated era, you don't have this effect. The gravitational potentials are constant over time in linear theory. The situation changes when the dominant component of the universe is not clustered. And so, for example, when you're in the radiation era, radiation dominates the energy density. It determines the expansion, but it's not clustered because of that pressure support. And so in that case, in this competition between expansion and clustering, the expansion wins and the potentials decay. And the same thing happens in dark energy domination. So dark energy contributes to the expansion, but because it's not clustered, it doesn't deepen the potential wells. And so the expansion wins and the potentials decay. So in these two periods of the universe's history, in the sort of radiation domination, or when radiation matters, soon after recombination, so radiation doesn't dominate, but it still matters. And then closer today, when dark energy start to matter and dominate, the gravitational potentials will decay. And so these are the two periods in the universe's history when you generate this integrated Sachs-Wolf. These are the two periods in which the potentials decay as the photons are traveling through them. And so on this plot, there's this curve which we call the early integrated Sachs-Wolf. And so this is this integrated Sachs-Wolf effect due to the presence of radiation after recombination. And then there's the late integrated Sachs-Wolf, and that one is the effect due to closer to today when dark energy starts to matter. A question? Yes?
What's the difference between the solid and the dashed line?
That's a good question. I'm not sure what the solid and dashed lines are anymore. I'm sorry about that. Mm-hmm. Yeah, I don't think that's something. This is clearly an effect mostly on large scales. So I'm not completely sure, yeah. Any other question on this? Mm-hmm. Mm-hmm. So why do you see a peak on sort of this angular scale? Mm-hmm. Yes. And so this is something I wasn't necessarily going to cover, but basically I'll leave this slide in the Google folder so you can take a look. Basically, what happens is which scales are enhanced by the ISW and which scales are not. You have your photon propagating through a certain distance, and the distance that's relevant here for the ISW effect is, for how long does dark energy domination occur, or for how long is radiation still important after the CMB. And on these scales, if you have fluctuations in the potentials that go up and down many times, the ISW effect is different if you go through an underdensity or an overdensity. And so if you have many bumps and wiggles during that period, the effect kind of cancels out. So the ISW will matter the most on scales comparable to basically that distance where radiation or dark energy matter. Okay, so this is all I was going to say about ISW. The next thing I wanted to talk about, and we've sort of alluded to it in the last two question sessions, I think, is the effect of reionization and this second bump in the visibility function. So if you remember the first lecture, the visibility function gives you what's the probability distribution function for the redshift at which any given photon might scatter for the last time. So what is the probability that a photon scatters at some redshift and then never again towards us? And we saw how this visibility function was peaked with a width that's basically the width of the surface of last scattering. But we also talked about how at some point the universe reionizes due to the ionizing radiation from stars, galaxies, and maybe quasars. And so that produces a second peak in that visibility function. And the result is that if you compute the optical depth due to that reionization period, you find that a small fraction, about 5 or 6% of CMB photons, is actually rescattered around reionization on its path towards us. And what does that mean for those photons to get rescattered? This is what I'm trying to illustrate with this light cone diagram. So this is time, and then you have 2 dimensions of space in that plane. And we live on this line where, say, we're not moving, and this is us today looking at the CMB. So that plane here is the normal surface of last scattering, so where the CMB was emitted. And the CMB we see is basically the intersection of our light cone with the surface of last scattering. If photons do not scatter again since the CMB, they just travel along the light cone towards us, and we just see the CMB the way it was. But if a photon is scattered again by some free electron around reionization, what happens is that this electron might take our CMB photon and scatter it out of our light cone. So we no longer see that CMB photon that we should have seen. And instead, that electron will scatter any other CMB photon from its last light cone and bring it to us. So what that means is during the scattering, the electron takes some light we should have seen and removes it and replaces it by other CMB light that we shouldn't have seen. And in doing so, it replaces the temperature you should have seen by the average of the temperature that it sees. And so what that does basically is if you should have seen, bright peak and dim position, so very hot spots and very cold spots, those hot spots will look a little less hot, and the cold spots will look a little less cold because some of these photons have been replaced by average photons at the average temperature. And so the net result from this is the temperature fluctuations you should have seen get multiplied by this e to the minus tau factor. And technically, this basically only occurs on small enough scales, scales that are smaller than the horizon size as seen by this electron. So basically on extremely large scales, there's no effect. And then on most scales, the power spectrum basically get brought down as you increase tau. And so since your temperature fluctuation have been reduced by a factor e to the minus tau, the power spectrum is reduced by a factor the square of that, so e to the minus 2 tau. And this is important, again, because if you look at the temperature fluctuations of the CMB and you're trying to use this to get a sense for what's the amplitude of the power spectrum of the initial conditions, the problem is that what you're seeing in the amplitude of those fluctuations in the CMB is not just the amplitude of the primordial power spectrum, it is reduced by this factor. And so while the amplitude of the CMB power spectrum, which is this whole thing, is extremely, extremely well measured, how well we can infer this parameter is completely limited by our uncertainty on tau. Any questions on this part? Yes. Right. Yes, and so the question was, so here it looks like on these scales, the damping is uniform. It's just this factor e to the minus 2 tau. But on large scales, on very large scales, there's no damping. Why is there this scale dependence of the damping? And it comes back to this diagram. And so I told you that when an electron at reionization scatters your CMB photon, it replaces it by the average CMB photon that it sees. And so it's not replacing it by just the full average. It's replacing it by an average on smaller scales, which are basically the scales of its horizon or its CMB size. And so, for example, this electron will replace your photon by the average on this circle. Another electron here would replace your CMB temperature by the average on this circle. And this average varies roughly on the scale of this. So anything that varies faster than this gets dampened, and anything that varies larger than this, if you replace it by the average on the same scale, doesn't get affected very much. Yeah. Yeah. Basically, what's the radius of that last scattering surface as seen by the electron? Is that scale? Yeah. Yeah. Right. And so to do this, it helps to be able to measure tau precisely. And that can be done best by using the CMB polarization power spectrum on large scales. So I don't think I'll have time to cover this today, but it's a really important thing. So thanks for asking. Okay. I'll skip this velocity overshoot, but you can read about it if you want on the Google Drive. And I'll just summarize sort of all the effects we've talked about yesterday and today to try to understand this CMB power spectrum. So again, here's our dimensionless power spectrum as a function of scale. And we talked about first this term in green here, that's effective temperature, is what we also call the Sachs-Wolf effect. So this is all that we talked about yesterday and quite a bit of today. And we talked about how there's those bumps and wiggles due to the baryonic acoustic oscillations. We talked about the asymmetry between even and odd peaks due to the effect of baryons. We talked about this radiation driving here in purple. It's often called potential envelope because it's a gravitational potential effect. So you have this radiation driving that amplifies the small scales. I think we talked last time about silk damping, which brings the power spectrum down. And then today we talked about the Doppler effect here in red, which also has these bumps and wiggles of comparable size, but out of phase because of this cosine squared versus sine squared. And finally, we talked about the Sachs-Wolf effect, which adds extra power on the larger scales in the CMB due to this decaying of the gravitational potential. And because this is also a gravitational potential effect, sometimes you'll see people group this integrated Sachs-Wolf effect with the radiation driving into one curve that they call the potential envelope, which sort of rescales the amplitude of the peaks of the CMB. And so when you add all these effects together, you sort of get the ISW bump, the Sachs-Wolf plateau, and the bumps of the BAO, the curve that you're sort of used to looking at. And clearly, you can see that there's a number of key angular scales that you can read off from this power spectrum. So the first scale is the acoustic scale. On which scale do you see those bumps and wiggles of the BAO? And so this, again, has to do with how far the sound can propagate between the Big Bang and the CMB. So by looking at the peaks and the troughs, you measure this acoustic scale. Then there's the scale at which the radiation driving amplification occurs. And last time we explained that this was when matter radiation equality occurs. And so this scale has to do with how much matter versus how much energy in photons or radiation you have. And then there's the scale at which this silk damping starts to occur, this diffusion damping. So again, that's another angular scale. And finally, there's the scale at which the integrated Sachs-Wolf effects start to matter. The scale here, which tells you something about since when did dark energy start to dominate. So a lot of angular scales you can measure from the CMB. And then the other parameters are the amplitude, the relative amplitude of the peaks for the effect of baryons. There's a few more things you could say about this power spectrum and what we learned from it. But maybe for today, it's already a lot, and so that's a good place to pause. I also want to advertise that there's a number of websites online, including this one, where you can change a number of cosmological parameters and see the effect on the matter power spectrum as well as the CMB power spectrum. And so it can be worth spending some time playing with these knobs and seeing the effect on the power spectrum. One thing I should warn you of, though, is that the effect of any different cosmological parameters when you vary it depends on what are the other parameters you chose to fix. There's different parametrization and different combinations of parameters you can do, and depending on what you fix, a certain parameter might have a slightly different effect. So if you get a bit confused by this, don't be alarmed. I'll spend the next few minutes before switching to polarization to just quickly go over the effect of various cosmological parameters on the power spectrum, to just remind you of all the things we talked about and how they fit together. Let's start with things like curvature or dark energy. One big effect of changing the amount of curvature or dark energy is for curvature, you change the geometry of space, and so you can make the angular size of the CMB spots appear larger or smaller. And so as you can see here, what you see on small scales is just a shift in angular scales. For dark energy, the same is true. If you change dark energy, you change the amount of expansion, or the rate of expansion between the CMB and us, and so you might change the distance to the CMB, which again results in rescaling along the angular axis. And then when you change the amount of dark energy, you will change the amount of integrated Sachs-Wolf on large scales. And what you're seeing here, I believe, has to do with how other parameters like dark energy change in this parameterization when you change curvature. When you change the baryon density in the universe, several things happen. One, the most noticeable one, is this asymmetry between odd and even peaks becomes larger when you have more baryons. So that's the baryon loading effect we talked about. Another slightly more subtle effect is you can see the peak shifts also horizontally in L. And that's this baryon drag effect we talked about how the speed of sound changes if you add baryons, which are just inertia. And another effect you see is the power spectrum gets changed on small scales. You're changing the amount of Silk damping, of diffusion damping, by changing the number density of free electrons. And then for matter, there's a number of effects you see. We talked about how when matter radiation equality occurs, changes when this amplification happens due to radiation driving. And by changing exactly where the amplification happens with respect to the first peak, you change the height of that first and mostly second peak. There's an effect in ISW, and I believe a lot of the effects you are seeing here might be due to other parameters changing at the same time, like baryons. Another way to look at it is if instead of changing the whole matter density field, you change the dark matter density. What you find again is this change in the peak heights for the first few peaks by shifting when that amplification due to radiation driving occurs. And I think that makes it clear that that's roughly the main effect. In passing, this is an important also evidence for dark matter. The fact that you have this radiation driving on some scales but not others means that you had this transition between radiation domination and matter domination, which could only happen if you have this extra matter, this dark matter. Other parameters, cosmological parameters having to do with the primordial initial conditions. So AS, the amplitude is trivial. It's just a multiplicative factor, so it goes up and down. NS is the spectral tilt of the scalar perturbations, and so it really just tilts the overall CMB power spectrum when you change this parameter. I won't say too much about current measurements of parameters in detail, but I'll just advertise papers like from the 2018 Planck cosmological parameters. And you can see that the parameters that are being fit are only around 6 or so parameters. And from these 6 parameters, you can derive pretty much all of the others. But I would encourage you to look at this Planck 2018 cosmological parameter just to get a sense for what are the typical uncertainties on the cosmological parameters. So the impression I'm trying to give to you is there's a lot about cosmology you can learn from just the CMB power spectrum, and in many cases, the precision at which you measure things is really incredible. So if you look at, for example, this theta here is roughly the angular scale of the acoustic peaks, and that number is 1 plus or minus something 10 to the minus 4. So you have extreme precision on a number of cosmological parameters. And we talked last time about this concept of cosmic variance and the fact that you only measure so many Fourier modes. There's only so many Fourier modes you can measure in the sky. And so as far as temperature is concerned, Planck measurements are almost cosmic variance limited in temperature. So you can improve those cosmological parameters a little bit by improving your sensitivity on small scales in temperature. But the main gain for these cosmological parameters will be to improve the measurements in polarization, where Planck is not cosmic variance limited. And so this will be the motivation now for switching to talking about polarization. So again, summary of what we talked about, the observed properties of the CMB and its power spectrum. We talked about Cartesian and angular power spectra last time. We talked about how the CMB fluctuations we see in the power spectrum today are the results of initial conditions from inflation, processing by the plasma with extremely rich phenomenology, as well as how these photons propagated from the last scattering to today. And hopefully we built some intuition for how by just looking at the CMB power spectrum, we can learn a lot of different things and how cosmological parameters affect the CMB power spectrum. So this is all I was gonna say about temperature fluctuations, and I'm now going to switch to polarization unless there's some additional questions for now. Mm-hmm.
Yeah, I'm sorry. So the rate ISW is triggered by the transition to dark energy.
Mm-hmm.
If you have more dark energy, that means that this transition happens earlier.
Mm-hmm.
So the large scales now moving more energy into dark energy.
So yeah, so you will see, yeah, that's right, you will see.
So my question is,
Mm-hmm.
why exactly does that imply the intensity of the spectrum of this wave? I'm
Right, so like why more or less ISW? Yeah.
because it's a peripheral also.
Right. So I mean, I guess naively, in the limit where there would be no dark energy at all, you would have none of this ISW. So that's kind of a plausibility argument for why more dark energy would be more ISW. The other effect is it changes the scales that are enhanced due to, again, this cancellation. So if dark energy occurs over a larger time scale, you will have cancellation unless you're looking at even larger scales.
Talking about the decay of the bucket, right?
Mm-hmm. Mm-hmm.
Which cancels the cancel effect,
Mm-hmm.
which would imply more mass environment. And since there is the decay in the dark energy emission era, and more dark energy implies that this era starts earlier, you have an enhancement.
Mm-hmm.
Trying to
I think that makes sense, but we can think about it more and talk about it. Yeah. And I should say another effect that I haven't talked about, which is still kind of an integrated Sachs-Wolf, and sometimes it's called the Riesz-Schama effect, is sort of the opposite effect, where on large scales in dark energy domination, the potentials decay. On very small scales, the scales of individual halos, some of these halos are still accreting mass, and their potentials are actually deepening. And so the enhancements in the photon energy you see on large scales, on small scales turns into a loss of energy. So the effect switches side. But that's an effect you'll see on much smaller scales. But yeah, thanks. Mm-hmm.
So by varying the cosmological parameters,
Mm-hmm.
get like different shape of the power spectrum, right?
Mm-hmm.
By measuring the power spectrum, you can get the cosmological parameters.
Right.
But also notice that if there is like different combinations of cosmological parameters that can get the same shape of the power spectrum, in that case, how do
Mm-hmm.
we know which one is correct?
Right. So yeah, so this is the question of sort of degeneracy between parameters. And can you fool yourself by producing the same power spectrum with different combinations of cosmological parameters? So last time there's one important degeneracy we talked about, and that's that geometric degeneracy. So you can change the distance to the CMB, and you can change curvature accordingly if you want, to keep all the angular features the same size. And so that's an almost perfect degeneracy from the CMB alone. And so that you will typically only break by using other late time observables, whether that's CMB lensing or BAO or other forms of lensing. And then there's some features of the parameters that are very non-degenerate with each other. So for example, the odd-even peak asymmetry is hard to mimic with anything else than baryon. The scale, at which the enhancement happens due to matter density is fairly distinct as well. So yeah, I think the geometric degeneracy is the main one. The second big one is amplitude of scalar fluctuations and optical depth, like we talked about. So to my knowledge, they're the biggest ones. Yeah. Cool, thanks a lot. Okay, so moving on to CMB polarization. Okay, CMB polarization fluctuations. So again, we talked about what is the CMB, the temperature monopole, the thermal history of the universe, recombination, last scattering. We talked about temperature fluctuations and this very, very rich phenomenology. And today we're going to talk about polarization fluctuation. And so that topic is pretty much almost as rich as the temperature fluctuations. But because of time, I'll try to be a bit more schematic and intuitive. And I'll try to simplify and give you as much intuition as possible. And then if you want the formalism, feel free to use any of the references I listed in the first slides. So what I hope you'll learn from this lecture is that the polarization we see in the CMB is generated by Thomson scattering of quadruples in intensity, and I'll explain what that means. I'll explain that those are caused basically just by velocities at the last scattering surface. I'll explain this concept of E and B mode decomposition, what the power spectra, the auto and cross spectra of these quantities look like, their features, and why would primordial B modes be so important if detected. So here's a map of the CMB produced by ACT this year in this paper led by Sigurd Næss and the ACT collaboration. In color, what is showed is the CMB temperature, and then the little black lines that you see everywhere, their orientation indicates the orientation of the linear polarization, and the length of each stick is the amount of polarization. And so you can see that the CMB clearly has fluctuations in polarization. That polarization is linear. The CMB does not have circular polarization, as far as we know. And the polarization is at about the 10% level. There is a correlation between temperature and polarization, but it's too weak for you to be able to see it at the map level here. You will see it very, very clearly at the power spectrum level, though. So to tell you how this polarization works, I first have to tell you what we mean exactly by polarization and how we describe it. And in CMB field, this polarization is typically described by those Stokes parameters. And in the Stokes parameters, you can define them. You can, as a function of the components of the electric field of the light that you see along two axes. And so these axes might be X and Y like this, so two arbitrary axes. You can measure the amplitude EX of the electric field along the X-axis or EY along the Y-axis. And if you just take the sum of the squares, you have the total intensity of the light. This is the thing that we convert into temperature when we talk about CMB temperature maps. And then you have two Stokes parameters describing the polarization. And so these Stokes parameters are the difference in the intensity along two different axes. So Q is along the vertical minus horizontal, and U is the same thing but rotated by 45 degrees. And the reason you need two scalar quantities to describe this polarization is because this is typically what you get for a spin-2 field. A spin-2 field is a tensor. So a spin-1 field is a vector, so a line with a certain direction. Polarization is a line but without direction. So it's a field where if you rotate it by 180 degrees, nothing has changed. So that's a spin-2 field. And you will need two scalar quantities to describe it, just like when you look at the galaxy lensing shear, for example, or the ellipticity, which is a spin-2 field, you'll need two numbers. And so for linear polarization, we quantify these these parameters, Q and U. And then V would describe circular polarization and is therefore not relevant for us here in the CMB. And so, for example, if you consider light where Q would be positive, but U and V would be 0, this corresponds to perfectly polarized light in the X direction. If you change the sign of Q, but you keep U and V 0, you also have perfectly polarized light, but in the perpendicular direction. The same is true for U, except shifted by 45 degrees. And so when we make maps of the CMB polarization, we basically make maps of the Stokes parameters Q and U. And if you make such maps and you look at them, so here's a Q map made by ACT, and here's a U map made by ACT. Something that might strike you when you look at these maps is they don't quite look like the CMB temperature maps in that you had blobs that were on average circular with no preferred direction. If you stare long enough at these maps, you might be able to see that there's sort of patterns in plus shape here on the Q map and patterns in cross shape here on the U map. And this is not noise or scanning strategy. This is really what happens when you measure the Q and U of the CMB. And so is there a preferred direction in the CMB? No. What's happening is that Q and U have a preferred direction in them. And it turns out for E modes, which I'll explain in a moment, for a pure E mode field, a Q map will always look like a checkered pattern like this, and a U map will always look like this. So what do we mean by a Q, an E or a B mode? So this is what I'll explain schematically here. So as I told you, these Q and U parameters have an issue, and that's the fact that they're coordinate dependent. If somebody chooses their X and Y axis like this, or if they choose them rotated by a certain angle phi, they will get different values of Q and U, rotated by an angle of 2 phi. And that sort of makes sense. Q and U are sort of rotated by 45 degrees. So if I were to change my coordinates by rotating by 45 degrees, I would sort of replace Q by U and vice versa. And so one interesting question is, can you replace those two scalar functions by two scalar fields that wouldn't be dependent on your coordinate choice? And it turns out you can if you define your E and B field, Fourier mode by Fourier mode, as a rotated version of these Q and U. And so here you see a rotation matrix very similar to above, basically undoing this rotation. And so you can measure those E and B fields from Q and U. You can invert this and get the Q and U field from E and B. These are equivalent quantities. If you give me a Q and U field, you've told me everything I need to know about linear polarization. If you tell me E and B, the same is true. Right, sorry. So this derivation here is flat sky because I'm talking about Fourier modes, just because it's easier to write. But this generalizes very straightforwardly to curved sky. Right, so the angle here, phi L, is an angle that's different L by L. And that angle is just the angle between your x-axis in your coordinate system and where the L vector is. Yeah, so I'm going a bit quickly through this. There's a very good reference, I guess, where this was actually derived. But so once you transform these Q and U maps into E and B, you can ask what does a typical E mode look like and what does a B mode look like. And the reason they're called E and B mode is sort of by analogy with an electric and a magnetic field. And of course, it's not a very good analogy because those are vector fields, whereas polarization is a tensor field. But if you look at a plane wave of E mode, so a plane wave, again, has a wave vector k, and it's constant in surfaces perpendicular to k. And if you look at what the polarization direction will look like for an E mode, you'll see that the polarization will alternate from being perpendicular to k, parallel to k, perpendicular to k, parallel to k. That's an E mode. If you do the same thing for a B mode, if you take that same plane wave but for a B mode, you'll find that instead the polarization direction will be at 45 degrees with respect to the k direction. So an E mode is something that, if you look at the direction along which it varies, the polarization is either perpendicular or parallel to that direction. And a B mode is, if you look at the direction along which it varies, the polarization direction is at 45 degrees. That will matter very soon because of what kind of initial conditions can produce E or B modes. But for now, of course, it may not be clear. Another thing to note is that E modes are basically parity invariant. If I mirror this image vertically or horizontally, nothing changes. Whereas B modes are pseudo-scalar in the sense that if I mirror this bottom image, if I flip it horizontally or vertically, it will look the same except wherever it initially, the polarization was like this, it'll be like this. Wherever it was like this, it'll be like this. And so the B mode basically changes sign as you mirror it. So this is what a B mode looks like for a plane wave. Here is what a B mode or an E and B mode might look like for a more complicated field. And so for a plane wave, what we said is, there's this special direction k, which is the direction in which the plane wave varies. And E modes are perpendicular or parallel, B modes are 45 degrees with respect to that direction. So for any more complicated field, you still have the same where, say this is brighter here and dimmer on the outskirts. Those arrows here represent sort of the local k, meaning the directions along which the E mode varies. And you can see in this case that if you look along the directions where the E mode varies, the polarization in this case is always aligned. If I flip the sign, it would always be perpendicular, but it's never at 45 degrees. It's either parallel or perpendicular to the direction along which it varies. On the other hand, if you take the same scalar function, but it's a B mode instead of being an E mode, you still have the same direction along which the field varies, but the polarization direction is always at 45 degrees with respect to that direction. And so that's sort of why this decomposition was called E and B mode. So for a vector, you can decompose the vector into a gradient and a curl. The gradient is kind of like an electric field. And for a gradient, the direction of the vector is always parallel to k. And then for the curl, the direction of the vector is always perpendicular to the gradient as opposed to 45 degrees. So that's where the analogy between B and magnetic fields breaks. Okay, so then because these E and B modes are independent of the choice of coordinate axes, they are a better quantity to look at and try to model. They're also a much better quantity to look at than Q and U, theoretically, for reasons that I'll explain very soon. But you can ask, what are the measurements of these paraspectra of temperature E and B? And so the CMB temperature paraspectrum we talked about at length yesterday and today. And then once you have this E mode map, you can take its auto spectrum, and this is what this curve looks like. And you can also cross-correlate the E mode map with the T map, and you get something like this, where the sign alternates. And then you can ask, what does the B mode paraspectrum look like? And the B mode paraspectrum has one dominant component that's actually due to gravitational lensing of the E modes. And so I might be able to say a few words on this tomorrow, but in any case, I'll talk about CMB lensing tomorrow. And so the idea is if you take a pure E mode polarization field and you just move where the positions are by lensing, you generate B modes. And this is the dominant part of the CMB B mode paraspectrum. And interestingly, the CMB B mode paraspectrum may contain an additional contribution from inflation, which I'll talk about in a bit. Okay, so far I've not talked about why there was polarization or anything like this. I've just talked about how one would describe a polarization field with those Stokes parameters Q and U, and how a better combination is those E and B modes of the polarization. And I've shown you what we observe those paraspectra to be. But now I would like to switch gear and tell you why the CMB has polarization at all, why we would have E mode and or B modes being generated. So I don't know if there's any questions before I start with this. Yes? So yeah, so in practice, what you measure is really the Q and U. And so if you remember the definition of Q and U, they're the difference in the intensity polarized in one direction minus the other. And so in practice, that's what you do. You have in your telescope, you have pixels, and each pixels you have sort of two antennae in two different directions. And so you measure the amount of intensity polarized along one antenna or the other, and you subtract the two. So really, you measure Q and U, and those Q and U maps are dependent on your coordinate system, and then you can convert these maps into E and B. Thanks. Yes?
What about the spectrum?
Mm.
As measured,
Right. Right, that's a really good question. And actually, yeah, thanks for asking, because there's something I should have said is, so it turns out, as we'll see, there's a non-zero correlation between the E map and the T map. And so naively, the way you can think of it is, so you measure the intensity map, that's your temperature map, and then you measure those Q and U maps, you convert to E and B. You obtain an E map that you can then cross-correlate with temperature. But something I haven't shown here is the power spectrum. Why can't you do the same thing with B and cross-correlate T and B? And this power spectrum, this cross spectrum, is actually zero because of symmetry. So I mentioned that the B mode changes sign when you flip it, when you do a mirror symmetry. It's a pseudo-scalar. And if you think that mirror symmetry should be a good symmetry of the observable CMB, and in practice it seems to be, you'll find that this causes the TB power spectrum to be zero always. Thanks a lot. Okay. So now I'll switch gear to the really fun part, which is why the CMB is polarized and what generates this polarization. And what generates the polarization of the CMB is Thomson scattering again. And this is an expression for the differential cross-section as a function of solid angle for where you scatter the light. And there's some fundamental constants like the charge of the electrons. There's an important parameter here, which is the mass of the object that does the scattering, so the electron. And as I mentioned the first time, this is why we mostly think about scattering of photons on electrons and not on the protons, because the electrons are much less massive by a factor 2,000. And so you have much more scattering with the electrons than the protons. Okay, and then you have this term that depends on the angle between the incoming and outgoing photons in your scattering. And the reason you have an angular dependence here, you have two terms, it's because there's two polarization. And so when you have the incoming and outgoing photons, those two lines define a plane, which unfortunately is not this plane here. They define a plane, and the polarization direction across that plane is just scattered with no modification. That's the one term. And then the polarization direction in the plane of these two lines, on the other hand, gets affected in the scattering. And so this is why you often get, when you look at reflections in a window, you often get polarized lights. And this is why, polarized sunglasses can help you when you look over the sea or when you look at reflected lights on buildings. And so if this is your glass panel, as this light here gets scattered along the glass panel, you can see that the polarization across is not modified, and the polarization in this direction can be altered, and in some cases, even completely nulled. One way to understand this is sort of the following, and so again, I would encourage you to stare for hours at the great animations from Wayne Hu's tutorials. So here's an electron and incoming light with the two polarization directions. And you can heuristically think that, that light, that electric field is making the electron oscillate and causes it to re-radiate light. And in this diagram, you can see that only the vertical polarization gets transferred toward us. Heuristically, one way to think about it is when light travels, the polarization of the light always has to be perpendicular to the direction the light is traveling. And so the incoming polarization in this direction would be parallel to the direction of the outgoing light. And so that polarization is nulled. So this is how, intuitively, Thomson scattering can generate polarization. In practice, the way it works is, in this animation, the polarized light you see in this direction is coming from this direction. And the polarized light you would see in this direction would actually be coming from there. So if I play these two animations, nothing has changed for the blue, only this component gets transferred. But for the red, a similar thing occurs where only that polarization direction comes out. So what you see is when I look at the light that's being scattered by this electron, the horizontal polarization is from the light coming here, and the vertical polarization is from light coming here. And so if you have more light in this direction than in that direction, the outcoming light will have a net polarization. And you can extend this diagram by seeing that whether the light is coming from the left or from the right makes no difference, and whether the light is coming from the top or the bottom makes no difference. So you will generate polarization when the light coming from left or right is more than the light coming from top and bottom. And that's what we call a quadrupole. More light from here than from there. So in order to generate CMB polarization, what you need is the electrons that do the scattering to see a quadrupolar distribution of intensity. So Thomson scattering converts quadrupoles at the surface of glass scattering into linear polarization. This alone is enough information to understand what type of initial conditions can generate E or B modes. And this gets probably very confusing. So I'll go through this, but don't worry if you're not following. I think this takes a lot of looking at drawings and making drawings to convince yourself that this might be true. And so if you look at scalar perturbations, so you've learned that inflation produces scalar perturbations that are like gravitational potential fluctuations or density fluctuations. And it also generates tensor perturbations, which are gravitational waves. So if you focus first on the scalar perturbations, typical scalar perturbation, if you look at a plane wave of it in 3D, maybe the k vector is in this direction. And that means that the field or the potential is uniform on planes where the CMB might be hot, and then cold, and then hot. And what that does is if you consider an electron here and you ask, what kind of light is this electron seeing? In this plane, it is seeing cold light. And when it looks up and down, it is seeing a hot light. And so this will generate a net polarization. And the polarization will be in this direction. If instead you looked at an electron in this upper plane, the situation will be reversed. It would see hot light from around it and hot and cold light from top and bottom. And so the polarization would be in this direction. And if you look at this pattern of vertical, horizontal, vertical, that varies in the vertical direction, that's an E mode. On the other hand, if you consider tensor perturbations, like gravitational waves, if a gravitational wave is propagating in these vertical directions, in the planes here perpendicular to that direction, where the gravitational wave is constant, the gravitational wave actually itself is a quadrupole, so it sort of compresses in one direction and stretches in the perpendicular one. And so an electron in that plane will actually see a quadrupole distribution, but that one can have any orientation within that plane. And so I can look at this electron, I could look at the one above or below, and I would see that the polarization direction alternates like this, which means it is aligned with 45 degrees with respect to the direction in which it varies. And so that's what you call a B mode. So this, I'm sure, is very confusing. Please take a look at it afterwards to try to see what this means. The thing I want you to remember is that scalar perturbations from inflation can only produce E modes, whereas tensor perturbations will produce both E and B modes. I will not talk about vector perturbations. They turn out not to be that important in practice. Okay, so if we go back, why is the CMB polarized? In temperature, we talked about Sachs-Wolf here, and integrated Sachs-Wolf. Those ones do not generate polarization out of unpolarized light. And so all the polarization we see is indeed due to that Thomson scattering process I described, where an electron seeing a quadrupole would then generate a linear polarization. We talked briefly about how those quadrupoles might be aligned or produced by scalar and tensor perturbations. Um, an important point I should explain is that if you are in perfectly tight coupling, in the tight coupling approximation, which has been our approximation for this study of sound waves in the plasma, in tight coupling, if you're perfectly tightly coupled, the mean free path of photon is 0. And in that regime, electrons will not see any quadrupole. So if you have perfect coupling and you have perfect blackbody radiation seen by your electron, the light intensity is the same in all directions. And so for the electron to be able to see any quadrupole at all, you need the mean free path to not be 0, and so you need to not be in perfectly tight coupling. And so what that means is that polarization will only be generated right around the last scattering. Because before this, the coupling is too good. There's no quadrupoles for electrons to see. And after this, there's just no more scattering, and so no more generation of polarization. Right, so you need imperfectly tight coupling to generate polarization. And then you need velocity gradients. And so the way this works is that a velocity gradient is a statement about differences in velocities. So if I'm the electron, the velocity gradient around me tells me how the neighboring objects are moving with respect to me. And so if I have a non-zero, if there's a non-zero velocity gradient, in practice, in this direction, it means that I see objects in front of me coming towards me and objects behind me as well coming towards me. And so that means I'll see more light in front and behind me than I see around. And that's a quadrupole. So the quadrupoles that electrons see are determined by the velocity gradient times the mean free path, meaning the mean free path is where I am looking. As an electron, I see photons coming from as far away as the mean free path of photons. And so the question is, what are the velocities of these photon fluids with respect to me? So velocity gradient times mean free path. And so in Fourier space, a gradient is just a k. And the velocity, as we talked about for the Doppler term, it was just a derivative of the temperature. And so that will tell us something about the shape of the polarization power spectrum with respect to the temperature power spectrum. Namely, you have an extra factor of k that'll give you an extra factor of L that tilts the power spectrum. And the time derivative, again, is going to turn a cosine into a sine and shifts the phase of the acoustic peaks. It turns out temperature gradients themselves at the surface of last scattering do not produce quadrupole at this order in the mean free path, only higher order and therefore smaller. Okay, and then the amount of polarization you generate is how much of a quadrupole do the electrons see times how much scattering there is during the width of the last scattering surface where this coupling is not perfect but still existent. And this sort of how many scatters do you see is the inverse of the mean free path. And the quadrupole we expressed above as a mean free path times the gradient of velocity. So the mean free paths cancel, and the amount of polarization is just gradient of velocity times width of the last scattering surface. And again, gradient is k times v, and v is the derivative of temperature. So basically, what I'm trying to tell you with this complicated reasoning is that the polarization we see in the CMB is a measure of the velocity gradients at the surface of last scattering. So if you remember, the temperature map shows you gravitational potentials at the surface of last scattering. The polarization instead shows you velocities at the surface of last scattering. Okay, I'll skip over this, but I'll use the reasoning we just made and this relationship between polarization and temperature, so the extra factor of k and the phase shift in the BO peaks, to understand what the E-mode power spectrum looks like. So again, polarization has this factor of k and a time derivative with respect to temperature. And so when you square it, you get a k squared, which once you project it is an L squared. And so at low L, you can see that if this is the shape of the temperature power spectrum, the shape of the E-mode power spectrum is tilted by a factor L squared, so tilted in that direction. And then this time derivative, will turn a cosine into a sine. And so when you square it to get the power spectrum, you find this cos 2x and minus cos 2x, meaning the peaks and troughs of EE and TT are shifted. So wherever you have a peak in E, you'll have a trough in T and vice versa. And then once you cross-correlate T with E, you get a cosine times a sine, so sine 2x over 2. And so you get something that whose sign alternates, and something which is in quadrature. The peaks are offset by pi over 2 with respect to temperature and polarization. Okay. In the interest of time, I'll probably skip this discussion of acausality of the initial fluctuations. Feel free to read about this later. But the short summary is one of the predictions of inflation is the existence of fluctuations on very large scales, much larger than the horizon at the time of the CMB. And so that is verified just by seeing a non-zero, for example, temperature power spectrum on very large scales. But another feature that's verified is what people often refer to as acausality, which is to say you would naively expect that if you have an overdensity here, it's because stuff has been moving in that direction. This is how you would causally produce this overdensity. But in practice, on large scales, you find that the sign of the velocity with respect to the temperature can alternate. And this is what you see in the CLEE power spectrum. And so this in itself is sort of an important check of a prediction from inflation. Okay, so we've talked about TT, we've talked about EE and TE. I would now like to shift gears and tell you about the B-mode power spectrum. And so, as I mentioned, the B-mode power spectrum that we observe is actually dominated by the effect of CMB lensing. So how if you take a pure E-mode map and you just shuffle a bit the positions of the positions on the sky, you will generate B-modes. And these are the B-modes you see here. But very interestingly and tantalizingly, inflation produces tensor modes, which, as we've discussed, should also generate B-mode polarization. And we can sort of understand the shape of this B-mode power spectrum by the fact that tensor modes decay once they enter the horizon. And so the power spectrum drops off fast past this scale of the horizon at the CMB. So this component of the B-mode power spectrum has not been detected yet. And so instead, what we have are upper limits on this little R parameter, which is the tensor to scalar ratio, the ratio of the amplitudes of the tensor and scalar power spectrum. And these constraints will continue to get better in the future with upcoming experiments like, actually ongoing experiments like Keck Array and Simon's Observatory. I just wanted to say a bit more about how important those primordial B-modes would be if they were detected. And these are statements about inflation. So of course, for the experts in the room, please feel free to correct anything I'm saying here. But yeah, the existence of those primordial gravitational waves, which produce primordial B-modes, is a generic prediction of inflation. And a detection of a significant level of those gravitational waves would put some pressure on some alternative models different from inflation. For example, bouncing models where the amount of gravitational waves produced should be very small. I would also argue that it would be a really amazing thing to detect. I think gravitational waves are an amazing thing to start with, and we're all very excited when they were directly detected by LIGO. But I think these are not your standard gravitational waves. I would argue these are even cooler gravitational waves because they come from quantum fluctuations in the space-time metric itself, as opposed to just two massive objects orbiting each other. So I think these would be extremely cool gravitational waves. And my understanding is that these would be evidences that gravity behaves like a quantum field, where you can derive those quantum fluctuations of the metric. And as far as I know, the cosmic microwave background is the best and perhaps the only way to measure these primordial gravitational waves if they exist. And finally, if you were to detect them and quantify this little R parameter, so the amplitude of the B-mode power spectrum, in some simple models for inflation, it would give you some very clear information. So in the case of single field slow roll information, for example, it tells you roughly at what energy scale inflation occurred and by how much the inflaton field would have had to shift during the slow roll. So this is most of what I wanted to tell you about CMB polarization. So polarization is generated by Thomson scattering of quadrupoles. These quadrupoles are produced by velocity gradients at the last scattering surface. And these quadrupoles are seen only once the tight coupling starts to break down. A good way to decompose or describe a polarization field, in this case, is E and B modes. It is good because it's independent of your coordinate system, and it is good because it lets you distinguish from primordial scalar perturbations and tensor perturbations. And so it gives you, in the form of this B mode, an almost null channel to see tensor perturbations. Not quite null, again, because of CMB lensing. We talked about the features of, the TE, EE, and BB power spectra, and the significance of primordial B modes if they were to be detected. And I was going to stop there, but since I have a bit more time, I would like to say a bit more about this optical depth tau and how it's measured. And so maybe I'll go back to the previous slides just for a second. So I mentioned that to generate polarization, you need scattering off of electrons. And the last scattering off of electrons happens mostly at the last scattering surface, where the CMB was emitted. But as we've talked about, there's another possible moment when scattering can occur, and that's around reionization. And so does the Thomson scattering around reionization also produce polarization? Question? Right. So that's a really good question. To just quickly answer, so the first reason why it is hard is you can see all the orders of magnitude on this y-axis. And so here, the CMB power spectrum is actually in microkelvin squared units. If you roughly take the square root of this, you get a number in microkelvin. And so you have to be able to measure extremely subtle changes in the temperature of the CMB as a function of position. And hopefully I'll say more about this in the very last lecture on how we actually measure the CMB and current experiments. But if you think about it, to measure the CMB, you're trying to measure a temperature. So really what you are doing is your experiment is a thermometer. You're trying to measure what's the temperature of this light. And you can have handheld thermometers that look at how much infrared radiation comes, and it gives you a temperature in Celsius. And you have to imagine that we're doing this experiment on the ground, on the Earth, which is at 300 Kelvin. And we're trying to measure the CMB, which is at 3 Kelvin. And we're trying to measure fluctuations in this at the level of 10 to the minus 5, so 100 millikelvin. That's to measure this. And then if you want to measure the B modes, you take the orders of magnitude here. You divide that by 2 if you want to take the square roots. That's the size of the typical fluctuations you're trying to measure. And so the CMB temperature fluctuations are 1 part in 10 to the 5 with respect to the mean CMB temperature. They're 1 part in 10 to the 7 with respect to the temperature in this room. And then you have quite a few more orders of magnitude to get at those B modes. So the way I think of it is, if you think about those handheld thermometers that look at infrared light and give you a temperature, imagine being inside of your oven. The oven is on, and you're inside it with that little thermometer. And across the room, the freezer is open. And you're pointing that little thermometer gun at the freezer. And you're hoping to measure the temperature of the freezer by getting only that very cold light not all the super hot light from the oven. And doing that is actually a lot easier than measuring the CMB temperature fluctuation and polarization fluctuations. So that sort of gives you a sense for how hot those measurement is. But hopefully we'll talk about it more on Friday. Yes? Mm-hmm. You're completely right. And so here I was only talking about just having the sensitivity to even measure those small temperatures. And this is something that's solved with quantum sensors and extremely good shielding from the Earth and its atmosphere. But like you say, there's also a lot of components that are actually on the sky. And so the sky has some polarization to it at these frequencies. And so there's many foregrounds that can contaminate your measurements. And so I'm hoping to talk about them tomorrow and Friday. But these are extremely important challenges because if your issue is the sensitivity of your instrument, in principle, you can always build a better instrument. If your limiting factor is a foreground that's on the sky, you probably cannot remove that one. And so your only option is to just model it extremely well, which can be very hard. So that's a really good point. Okay, so I'll go back to this question of Thomson scattering at reionization and whether it can produce polarization. And so again, what we said is that for Thomson scattering to produce polarization, you need the electron that's doing the scattering here to see a quadrupole. And so if you think about it in this light cone, the electron here that's doing the scattering is seeing CMB light on its own CMB. So we see the CMB. The electrons at recombination, at reionization, also see a CMB. They're a bit closer to the CMB. But the CMB they see may have a quadrupole in it, just like the CMB we see has a quadrupole. And so when an electron at reionization sees its own CMB, it sees a quadrupole, and it will convert this quadrupole into polarization. And so indeed, there's a component to the EE power spectrum that's polarization, that's scattering of the quadrupole that the electrons see. And so we do expect a signal in the EE power spectrum from reionization. And this signal, the size of it, will be how large is the typical quadrupole that one of these electrons might see, and this is something we can quantify. And the other part is how many electrons are there here doing the scattering. And so this is why it's interesting, because on the larger scales, in the CMB EE power spectrum, you actually do see a bump from this effect, so the scattering of quadrupoles that electrons at reionization see. And by measuring the amplitude and the shape of this bump, this is actually our best way of inferring tau, the optical depth through reionization. So that's another important thing. Okay, so I think I managed to cover what I wanted to cover today, and so I have a few more minutes for question, as I'm sure all this polarization stuff was very confusing. Mm-hmm. So going back to the light cone. Oh, I'm sorry. Yeah, sorry. The annotations on this plot are confusing. This plot was actually talking about a different effect, and I'm just repurposing it for my purposes. So ignore this extra scattering. For our purposes, there's just the CMB traveling from the last scattering surface towards us, or the CMB that would have traveled to us getting scattered once at reionization. Yeah, so please ignore this other scattering here. Yeah, question?
So I want to know how can you measure the tensor to scalar radio without actually measuring the BMOS power spectrum?
Right, and so the answer is you don't measure the tensor to scalar ratio. You put an upper limit on it.
Yeah,
so you lower your noise as much as you can. You reduce your foregrounds as low as you can. you account for the effect of CMB lensing, and you ask what's the residual power spectrum in my B modes, and then you can convert this into an upper limit on R. So for now, all we have are upper limits, but the sensitivity is improving, bringing the upper limits down, with the hope of maybe detecting the effect. Yep.
I have a question, maybe it's related. What was exactly the confusion of BICEP when they say that they measure that the primordial B modes? I didn't understand correctly, but it is because they measure like scales, the multiples, like between the intersection in the power spectrum of the primordial and the lensing?
Right, and so this is the point that was mentioned earlier at the back, is the fact that when you look at the B mode polarization of the sky at these frequencies, you're not just seeing the CMB, you are seeing other foregrounds. And on these large scales there, one of the dominant foreground is from our own Milky Way galaxy. And so you have thermal dust emission from our own Milky Way, and you have radio synchrotron emission from our own Milky Way. And those can produce some amount of B mode polarization. And so if you want to be able to measure the primordial B modes without confusing it with Milky Way, you need to either subtract the foreground from the Milky Way using multiple frequency channels, and you need to be able to model the residuals very well. And so the confusion there was basically confusing Milky Way foregrounds for primordial B modes. And the fact that the initial claim was at the level of R of 0.16 or 0.2 gives you a sense of how large the foregrounds is. That's the level of the Milky Way foregrounds, 0.16, 0.2. And so going below in R means reducing that foreground by large amounts. That's a really good point.
And another question is when you show that the quadrupoles are caused by these velocity gradients, and this happens when the tight coupling ends. Is that the reason why the recombination doesn't occur like in instantaneous time? It takes an amount of time to the recombination. Otherwise, we don't have polarization.
Oh, right. Yes, and so something I showed is that the amount of polarization you get is kind of proportional to the width of that last scattering surface. And so for the purposes of CMB temperature, if the recombination had been instantaneous, you would still see the CMB temperature fluctuations mostly unchanged. For polarization, yeah, the amount of polarization depends on the width of that last scattering surface.
Okay. Okay. Thanks.
Thanks.
Yeah, really quickly about what we're talking about, the foregrounds, right? So those astrophysical foregrounds, are they in general easier or more? I assume they are more challenging to subtract from the signal than the conversion of E modes to B modes due to lensing, for example. Is that correct?
Right, and so yeah, so the conversion from E mode to B mode, we have a good idea for what the CMB lensing power spectrum, and we have good measurements of the E mode maps and the E mode power spectrum. So one thing you can predict very well is what the expected B mode power spectrum should be due to lensing. And so that you can predict fairly well, and you can propagate your uncertainties to that measurement. In practice, people do a bit better than this. So they don't just predict what the lensing B mode power spectrum is and subtract it at the level of the power spectrum. Because if you do this, you have subtracted the expected level, the mean level of CMB B modes due to lensing, which means you haven't removed the cosmic variance. So perhaps the lensing field happened to be a bit higher here when the E mode was a bit higher. So the amount of lensing B mode you may get may be a bit more or less than the expectation value. And that difference is just cosmic variance. But so you can do better than subtracting the mean lensing B mode power spectrum. You can do something called delensing. And delensing is that if you have a good map of the E modes and you have a good map of the lensing field, you can actually generate an actual map of the lensing B modes, and you can subtract that actual map. And by subtracting the actual map, you've subtracted the cosmic variance of the lensing B modes. And so that's what delensing is, and it does better than just subtracting your guess for the lensing beam mode power spectrum. To do this, you do need to have a good idea of what the lensing map looks like. And that one you can do either by using CMB lensing measurements, which we'll talk about next week, or you can do by using large-scale structure surveys, because the galaxies in those surveys are correlated with the matter that's causing the lensing.
Thanks.
Thanks.
In the previous slides, I guess, where you showed the Planck's result with the cosmological constraints, there was also the low E.
Yes.
And I was wondering, how is it related with the polarization?
Yes. Thanks, that's a really good question. So, yes, so you can constrain cosmological parameters using temperature or using polarization, and then you use TE, EE. And then there's this sort of special thing that's called low E. And low E is the low L E modes. So these are, again, the ones that are produced during reionization when those electrons scattered the quadrupoles that they see. And the reason often you will see cosmological parameters with TT, but adding just low E, what this really means is you're just basically adding information on tau, the optical depth. So you can think of measurements with TT and low E as just being, this is the temperature power spectrum, and I've just used our idea of tau from EE. And then these measurements will include all of the temperature and polarization. And in this case, it also includes CMB lensing and BO measurements.
And is there any particular reason why we are using low E together with temperature, or and not just temperature, for example? Would we be able to infer information about the ionization? Yeah, we saw that we are able to infer information about ionization starting from TT. So why are we adding low E as a baseline?
Right. So I think what happens is that mostly in the temperature power spectrum is affected by tau. It is dampened when you increase tau. But we're not really inferring tau very well from TT. So the issue is that if you have TT alone, you have this, again, this large degeneracy between the amplitude of primordial fluctuations and tau. And so by including this low LEE measurement, which tells you what tau is, you break that degeneracy, and then you're able to use temperature to actually constrain AS, the amplitude of scalar fluctuations. So really the goal is just to have an idea what tau is to break the degeneracy between AS and tau.
Okay, if there is no more question, let's thank Manu.
Cool. Thank you.